Hi there. Today we want to talk about the one sample means with the t-distribution. We're going to do it through a slightly different example. So let's look at an example that looks at Friday the 13th. So between 1990 and 1992, researchers in the United Kingdom collected data on the traffic flow, accidents, and hospital admissions on Friday the 13th and the previous Friday, Friday the 6th. Below is an excerpt of this data set on traffic flow. We can assume that traffic flow on a given day at locations 1 and 2 are independent. Notice here we have 10 observations of Friday the 13th and Friday the 6th. Notice also we have a difference column where we take the difference as the value from the 6th Friday versus the 13th Friday. So we want to investigate if people's behavior is different on Friday the 13th compared to Friday the 6th. One approach is to compare the traffic flows on these 2 days. So we have a null hypothesis that would state that the average traffic flow on Friday the 6th and the 13th are not different, or they're equal. And the alternative is that the average traffic flow on these 2 days are different. Each case in the dataset represents traffic flow recorded at the same location in the same month of the same year. One count is from Friday the 6th and the other is from Friday the 13th. We ask ourselves, are these two counts independent? And the answer is no. Because they come from the same location in the same month of the same year, they would be dependent upon the location and the year. So what are the hypotheses for testing for a difference between the average traffic flow between the Friday the 6th and the 13th? Notice we have 4 options here. Option A is comparing two independent means. Option B is comparing two independent proportions. Option C is comparing the difference of means of dependent observations, and D is comparing the difference of sample means So when we look at these, we know that D is out of the question. We are never truly interested in sample information, rather we use that information to infer on the population. B does not make sense because we are dealing with averages, not proportions. And A doesn't make sense because our values are not independent. They are dependent. So C is the best choice. If this was a little bit confusing for you, don't worry. We will learn how to deal with independent and dependent means more in this chapter later on. So the conditions that we should check in order to do any kind of testing are independence, and we're told to assume that cases or rows are independent. We need to check our sample size and skew. So the sample distribution, which shown to the right, does not appear to be extremely skewed, but it's very difficult to assess with such a small sample size. Remember, we only have 10 observations going on here. We might want to think about whether we would expect the population distribution to be skewed or not. And the answer is probably not. It should be equally likely to have days with lower than average traffic and days that have higher than average traffic. But the biggest issue is our sample size is less than 30. So what do we do when the sample size is small? Well, what purpose does a large sample size serve? Remember, as long as observations are independent and the population distribution is not extremely skewed, a large sample would ensure that the sampling distribution of the mean is nearly normal, and the estimate of the standard error, which is the standard deviation divided by the square root of sample size, is reliable. The central limit theorem, which states that the sampling distribution will be nearly normal, holds true for any sample size as long as the population distribution is nearly normal. While this is a very helpful special case, it's inherently difficult to verify normality in small data sets. We should exercise caution when verifying the normality condition for small samples. It is important to not only examine the data, but also think about where the data come from. For example, ask yourself, would I expect this distribution to be symmetric? And am I confident that outliers are rare? When working with small samples, the population standard deviation is unknown, which is almost always true. The uncertainty of the standard error estimate is addressed by using a new distribution called the t-distribution. This distribution also has a bell shape, but its tails are thicker than the normal models. Therefore, observations are more likely to fall beyond 2 standard deviations from the mean than under the normal distribution. These extra thick tails are helpful for resolving our problem with the less reliable estimate of the standard error, since our sample size is small. Here you see a picture of a normal distribution as the dotted line and the t-distribution as the solid blue line. Notice the thicker tails, and notice the peakedness of the normal distribution compared to our t-distribution. The t-distribution is always centered at 0, like the standard normal distribution, and it has a single parameter, which we call degrees of freedom, denoted by df. In this picture, you can see that with small degrees of freedom, our t-distribution has very large tails, very thick tails. And as the degrees of freedom increase, we get closer and closer to what? A normal distribution. So back to our example. Here, if we look at our difference column, we can take the average of the differences and get 1,836. Calculate the standard deviation of the differences and get 1,176. And our sample size here is 10. We'll use these numbers in a bit. So we need a test statistic for inference on a small sample mean. The test statistic for inference on a small sample, which is usually when n is less than 50, is the t-statistic with n-1 degrees of freedom. To denote that we're using a t-distribution, we use t, and we denote the degrees of freedom as a subscript, but it's calculated the same way as a z-test statistic, which is point estimate minus null value divided by standard error. It's what we do with this test statistic that makes it different. So in context, our point estimate, which is the sample mean of the differences, is 1,836. The standard error, which is the standard deviation of the differences divided by the square root of our sample size, is 372. And our t is calculated as the point estimate minus the null value divided by the standard error, or 4.94. Our degrees of freedom is sample size minus 1. It should be noted that the null value is 0 because in the null hypothesis, we set that the average of the differences is equal to 0. This doesn't always have to be the case. The p-value is, once again, calculated as the tail area under the t-distribution. We could use a web applet to find this, or we could use our t-table, which you will be given. So on your t-table, to find a p-value, you want to first locate the t-statistic on the appropriate degrees of freedom row. You want to obtain the p-value from the corresponding column heading, 1 or 2 tail, depending on the alternative hypothesis. So in our example, we had 9 degrees of freedom. So we want to focus on the row with 9 degrees of freedom. Our test statistic was 4.94. And as you notice, as we read from left to right, the values get larger. Because we have a two-tailed test, we want to focus on the two-tail numbers. So what is the conclusion of our hypothesis test? Well, since 4.94 is greater than 3.25, we would expect our p-value to be smaller than 0.010. That is, at a 5% level of significance, the data provide convincing evidence of a difference between traffic flow on Friday the 6th and the 13th. So we concluded that there is a difference in the traffic flow between Friday the 6th and the 13th. But it would be more interesting to find out exactly what this difference is. We can use a confidence interval to estimate this difference. Our confidence intervals are always of the form point estimate plus or minus margin of error. Margin of error is always calculated as a product of a critical value and standard error. In our last chapter, our critical value was usually z star. Here, since we have small sample means that follow a t-distribution and not a z-distribution, the critical value is going to be t star. So, when we have a small sample mean, the confidence interval is point estimate plus or minus t star times the standard error. How do we find the critical t, or t star? We first want to look at the n-1, or 9 degrees of freedom row in this example, and we want to look at the two-tail. If we're looking for a 95% confidence interval, we want to go to the 0.05 row column, giving us the total left over after the 95% is in the middle. It's going to be the intersection of these two that yield our critical t of 2.26. So which of the following is the correct calculation of a 95% confidence interval for the difference between the traffic flow between Friday the 6th and the 13th? Remember, the sample mean of the differences is 1,836. The sample standard deviation of the differences is 1,176. Our sample size was 10. And if we take the sample standard deviation divided by the square root of 10, we get 372. So we have three choices here. We have A, B, and C. A is incorrect because that's using a Z star, not a T star. C is incorrect because that takes the point estimate plus or minus our T star, but it only multiplies it by the standard deviation, not the standard error. So our answer is B. And when we calculate this, we get a confidence interval of 995 to 2,677. So what is the best way to interpret the confidence interval? Well, if you remember, we take the differences as the 6th Friday minus the 13th. And that's where we got our confidence interval of 995 to 22677. So of these, we are 95% confident that on Friday the 13th there are 995 to 2,677 fewer cars on the road than on the Friday the 6th, on average. Another way we could have looked at this is that there are 995 to 2,677 more cars on the road on Friday the 6th than compared to Friday the 13th, on average. But in either case, our answer is D. So does the conclusion from the hypothesis test agree with the findings from the confidence interval? And the answer is yes. The hypothesis test found a significant difference, and the confidence interval does not contain the null value of 0. Do you think that findings of this study suggest that people believe Friday the 13th is a day of bad luck? Well, it should be noted this is an observational study. We just have to observe a significant difference between the number of cars on the road on these days. We have not tested for people's beliefs. So let's recap. If our sample size is small, sample means follow a t-distribution, where our standard error is equal to the sample standard deviation divided by the square root of n. The conditions that we need to check are the independence of observations, which is often verified by a random sample, and if sampling is done without replacement, we want to make sure that our sample size is less than 10% of the population. If n is less than 30 and there's no extreme skewness, we consider these conditions met. For our hypothesis testing, we still take the point estimate minus the null value divided by the standard error, and we call this t, where our degrees of freedom are equal to n minus 1. For our confidence interval, it is the point estimate plus or minus the t star with n minus 1 degrees of freedom times the standard error. It should be noted that the examples that we used was for paired means, or differences between dependent groups. We took the differences between the observations and used only these differences. We consider that to be our sample in our analysis. Therefore, the mechanics are the same as when we are working with just one sample.